So an object moves over time according to this differential equation, where x is the position of the object in meters relative to some reference point, and t is the time in seconds. So if this is like the position in meters divided by the time in seconds, that's velocity, okay? Velocity is measured in meters per second. So this differential equation is giving you the velocity of your object over time. So what we're asked to do is solve the differential equation. So that means we're going for whatever's on top here, x. We want to get x equals, or position equals, over time. So that's our ultimate goal here. So looking at this differential equation, we need to figure out how we can approach it to solve. And looking at it, what I would suggest is doing like the separation of the variables across the equal sign. So what I mean by that is on the left-hand side, say, what we want to get is everything with x's in it, and on the right-hand side, we want to get everything with t's in it, because they're the two variables in our equation. So let me just write out our equation to start with. And then let's go ahead and do that separation as the first step. So as I said, I think probably the easiest thing to do would be to shift anything with an x to the left-hand side, anything with a t to the right-hand side. So if I want to move the x squared to the left, it's going to end up being 1 over x squared. And I'm going to leave the dx here. And if I want to move dt to the other side, it's going to go to the top line. And I'm going to be left with the 5, t minus 2, and then the dt multiplied on the end. So now I have separated across the equal sign. What I should now be able to do is integrate both sides of my equation. And what this should mean then is that I get rid of this dx and dt and just get an expression with directly just x's and t's like we had up here on the right. Alright, so to make this process a little bit easier, on the left-hand side here, what I can do is instead of writing this as 1 on x squared, I could write it as x to the power of negative 2, just flipping it up to the top line. All that changes is the sign on it. And on the right-hand side here, what I could do if I wanted is bring the 5, it's just a constant, out the front. And then all I'm going to have to integrate is the t minus 2 inside with respect to t. Alright, so keeping on going here. So this is now a simple case where all I need to do to integrate is add 1 to the power and divide by the new power. So if I do that, I'm going to get x. Adding 1 to the power, it's going to go to negative 1. And dividing by that new power, I'm going to be dividing by negative 1. So for the right-hand side here, when I integrate, the 5 is just going to stay out the front. And then again, I can apply the same rule here. So this is t to the power of 1. I'm integrating it with respect to t. So all I need to do is add 1 to the power, which is going to make it t squared, and divide by the new power. Put a bracket in here since the 5 is multiplied by everything. And then here, this is like if we had t to the power of 0, because anything to the power of 0 is 1. So this would just go back to like 2 times 1. So again, if we add 1 to the power, it's going to go t to the power of 1, divide by the new power, which is 1. And since we have done indefinite integration, i.e. we have no bounds on our integration signs, we need to make sure we have our little plus c. And it doesn't matter which side you put it on, we only need one because they're just going to cancel each other out to form one constant anyway. I'm going to pop it on the right-hand side here. Alright, so now the challenge becomes rearranging this equation to get x equals. You can see that as we had planned, we have eliminated all the little dx's and dt's. So I can clean this side up. This is like negative x to the power of negative 1. And again, if you wanted to rewrite this even nicer, it'd be like flipping this down to the bottom line again. X to the power of positive 1, which is the same as negative 1 on x. Okay, so let's just go back and write this as negative 1 on x. Alright, here we've got 5 outside of, I'll just leave it, t squared on 2. And then this we can rewrite as 2, t to the power of 1 is just t, and dividing by 1 does nothing. So we get that. And now what I want to do is try and get x on its own. So what I'm going to do is multiply this up to the other side of the equation, and at the same time I'm going to divide this down. So I'm going to get negative 1 over 5 t squared on 2 minus 2t plus c. It's equal to the x that got multiplied up onto the other side of the equation. So this here becomes my equation, or solution to the differential equation. And what we can see is that we have this random constant c, which has been introduced. That's going to be a constant that you can only find if you're given some other condition, such as a boundary condition or an initial condition for your system. So if you're given at some point x is equal to something and t is equal to something, you're going to be able to go through and solve. But at this stage, this is the best that you can do. So that's the answer to that question.